All right, students, so this is our first lecture video on thermal physics. This is 3.1.1, and I'm going to talk about some pretty simple concepts here, and that is temperature and molecules, and then a little more complicated heat. You should have been exposed to these ideas before in your previous science courses, so a lot of what I'm going to talk about in this video hopefully will be review for you guys, okay? All right, so we're going to start simple and just talk about this idea of temperature. Now, you all know what it means when the day is hot and when the day is cold, and how to tell the difference between something hot and something cold, okay? But I just want to point out that in physics, the idea of temperature is simply a measure of the average kinetic energy of molecules inside of a substance, okay? So remember that every substance has molecules that are arranged in some particular fashion. So for example, solids are arranged in a tight, rigid lattice formation, liquids not so much, and gases, the density of those molecules, the mass per unit volume or the number per unit volume is relatively low, okay? And all those molecules are always moving, all right? So quite simply, the faster that they're moving, the higher the temperature. Now, temperature is a scalar quantity. We would never assign a direction to it. And the SI units that we're going to use for temperature, we can either use Kelvin or degrees Celsius, okay? And the reason why we can use both, well, you see temperature quantities in physics written as both, and the reason why we can use them as both is because the increments are equal. So for example, 1 Kelvin, the interval of 1 Kelvin is the same as 1 degree Celsius, even though the actual number designation might be different, okay? So for example, since temperature is proportional to average kinetic energy, as I increase the average kinetic energy, the temperature goes up and vice versa, okay? A couple of things about the Kelvin and Celsius scale. Notice that Kelvin goes down to 0, whereas Celsius can have negative values. I'll talk about that in just a second, okay? Converting between Kelvin and degrees Celsius, you just add 273 to your temperature in degrees Celsius. So obviously, if I go from freezing water to boiling water, that's a delta T of 100 degrees Celsius. That's also a delta T of 100 K. Remember, we also don't say degrees Kelvin, we just say Kelvin, okay? So this is the same as going from 273 to 373, which is 100 K. Absolute zero is defined as 0 K, which is negative 273. For the first example, I want you to just kind of estimate the approximate Celsius and Kelvin temperatures for the following. It's probably easier for you to do Celsius right off the bat. You have maybe a better sense of that than you do Kelvin. Go ahead and pause the video and try this one. Okay? Okay, so basically these are some very approximate numbers, okay? And in using these numbers, all I do is I add 273 to all of these numbers to get the temperatures in Kelvin, okay? So a big advantage of the Kelvin scale is that there's no way to have negative temperatures. And generally, as you know, we try to avoid negative values of anything if we can help it. That's why the Kelvin scale is so useful for us, okay? Okay. So we're going to get into something a little more difficult here, and this is the concept of heat, all right? So we've been spending a lot of time in this course talking about friction and about how energy is lost, and of course most of the time we ignore friction because it makes the calculations and the physics a lot simpler, okay? We did that in kinematics, for example, a lot, and especially dynamics. Now, if you consider a block here, this yellow block, as being pulled by a force F, okay? And it's being pulled specifically with a constant velocity, so no acceleration, okay? Now, how can that be that you're applying a constant force to something and it's not accelerating? The only way that that can be is if the net force on the entire block is 0. So there must be an equal and opposite force in this direction, and that is the force of friction. So we're no longer going to we're no longer neglecting friction in this particular case, okay? So if the sum of all forces is 0, then F equals ma, and the mass is obviously not 0, then the acceleration will be 0, okay? So there's some questions that we need to kind of think about here. Number one, is there any work being done on the block by this force F? Well, of course there is, because there's a force being applied through a distance. And remember, the work-energy theorem tells us that if there's work done on something, then that something is going to acquire energy, which will in turn enable it to apply a force or do work on something else, okay? So therefore, is energy being transferred to the block? Absolutely. Energy is being transferred to the block by this force. And I'm ignoring the frictional force right now. I'm just talking about this force, capital F, this blue vector pointing to the right, okay? All right, but is the kinetic energy of the block increasing? Well, of course it's not, because the velocity is constant as specified in the problem, having no acceleration. Is the potential energy of the block increasing? Now it's getting interesting. If you're talking about the gravitational potential energy, clearly in this case, no. But if you're talking about the potential energy between the molecules, now definitely there's something going on, right? Okay. The other thing to think about is my question about the kinetic energy. If you're talking about the kinetic energy of the block, or are you talking about the kinetic energy of the molecules? Turns out the kinetic energy of the molecules is actually increasing, and we'll see that why that is in just a second. Okay, so the question is, where is the energy going from this bullet point right here? Where is it going? Well, it's being dissipated as heat. So whenever you have friction, you have heat produced. You have thermal energy being transferred, okay? And this is a molecular sort of view of it through a PhET simulation of a chemistry book and a physics book being rubbed on top of each other. And you'll see that when you rub them back and forth, that the temperature actually goes up because it causes the molecules right at that contact point to jiggle more and more and more vigorously. Therefore, their kinetic energy goes up, and by definition, the temperature is going to go up. Okay? All right. Here's an example of a thermogram. You see these a lot. Be aware that when you see thermograms, they're not always scientific, but they're kind of interesting. Like this thermogram of this car shows that the car was probably very recently driven because there's more thermal energy being shown, or a higher temperature being shown in the wheels and the brakes than the rest of the car. Okay, so here's your physical definition of heat. Okay, and for heat, of course, we always use the term capital Q for heat. All right, and what it is it's simply the energy that flows between two objects as a result of a temperature difference. Okay, an object doesn't just have heat. Okay. I don't contain heat, you don't contain heat, but as soon as I touch something and there's thermal energy transferred from me to that something or vice versa, then that's what heat is, okay? If there's no temperature difference, there's no heat flow. Heat is also called thermal energy flow, and because it's energy, the SI units are joules, okay? You also see it expressed in terms of calories. That's the English unit for energy, okay? So again, something does not contain heat. Only when energy moves spontaneously between them do we use this term heat. Okay, so we need to also consider the total internal energy, or the internal energy of a substance, okay? In this class, this refers to the total amount of energy of all molecules in a substance, and it can be kinetic, potential, intermolecular forces, all these kinds of different kinds of energy, the sum of which we call internal energy, okay? Some other important things about heat transfer. Temperature determines the direction of thermal energy transfer, okay? There must be a temperature difference, and thermal energy, or heat, always flows from a hotter object to a colder object, okay? Naturally speaking. It's never going to be in the reverse of that, all right? Okay, if thermal energy does not flow between two objects, then they must be in thermal equilibrium and have the same temperature. Okay, so in this bottom case right here, you're not going to have any heat flow between these two objects. Okay, now thermal energy flow can be positive or negative. It's not a vector quantity. Okay, but it can be positive or negative, meaning that if an object has positive Q, it means that it's absorbing heat. If it has negative Q, it means it's giving off heat, or the heat is being transferred to the surroundings from that object. And there are three ways to transfer heat, and I hope that you've heard of these terms before this class. There's conduction, two things in contact. Convection, you can think hot air rises, okay? And radiation, which are electromagnetic waves through space, okay? All right, so for the second example, just go ahead and indicate whether Q is positive or negative for the following objects. Go ahead and pause the video and try this one on your own. Okay, so the object in question is the one that's underlined. A cola is cooled, negative. You heat your coffee, the coffee is positive. Pudding, negative. Hands, positive. You walk out into the sunlight. The idea is that you acquire thermal energy, so it's going to be positive for you. Okay, so just some review on molecular arrangements. This will be very important when we study kinetic theory of gases and the ideal gas law. We're also going to talk a little bit later about moles and molar masses and so forth. Okay, so just to remind you that a solid has a fixed shape and volume. A liquid has no fixed shape but a fixed volume, and a gas has no fixed shape or volume. And you should be familiar with these general characteristics of the three main states of matter. Okay, no matter what the state, intermolecular forces act between the molecules. These intermolecular forces are stronger in solids, weaker in gases. That's why solids are rigid and held tightly, and so forth. And again, for friction, when two objects rub past each other, the molecules actually vibrate faster and faster and are slightly further apart. And that's why when things heat up, they actually slightly expand. Okay, a couple of really important terms in physics that you need to know. And this is the idea of macroscopic versus microscopic. You think of macroscopic as something being in bulk. So for example, temperature is a macroscopic property. Microscopic is something that's very, very small on the atomic level. So you can think of the kinetic energy of molecules as being microscopic. It's really just a matter of scale. And here's a table that I want you to pause the video and really take note of this particular table about the difference between, here are some examples between microscopic and macroscopic properties, okay? Very, very important to understand the difference between them, okay? So in other words, macroscopic refers to things that are large enough to be visible practically with the naked eye, okay, without instruments or devices. So for example, you can tell that something's hot or cold without needing some sort of instrument to tell you that. Okay, microscopic is too small to be visible without instruments or devices. So for example, the orbital of an electron around an atom, you could never actually see that, right? So that's not macroscopic. That would be microscopic, okay? Another example, so the flow of water through a pipe is obviously macroscopic. We can observe that, its velocity, its pressure differential, and so forth, okay? However, the molecular structure of water, talking about the covalent bonds and the angles between them, that's microscopic, okay? And obviously, if you're a plumber, you probably don't really need to know the microscopic properties of water. Maybe you have a chemistry degree, I don't know. But what you are more interested in your plumbing practice is to understand how water actually flows through pipes, which is macroscopic. So depending on the application, which scale you're interested in can be very, very important.